Alright, good morning everyone. Today we're gonna follow up what we started yesterday with integration by parts. So the first thing I'm going to do right now is just gonna recap what we did yesterday for those of us who were either gone on Thursday or simply weren't paying attention. So let's start out with what integration by parts is. So integration by parts is used to integrate a product such as the product of an algebraic or a transcendental function. In other words, you're dealing with a product of usually a polynomial of some sort times, like it says, another polynomial, or in this case, a transcendental of some sort, or a trigonometric function. So to start off, we're going to go back to the the product rule to derive your formula for integration by parts. So if you have a function u and a function v, the derivative of u times v, according to the product rule, would be u prime times v. Okay, now that's the first part, plus u times v prime. So in other words, derivative of the first times the second plus the first times the derivative of the second. Now I'm going to take a moment over here to define u prime as du dx. Okay, so these are the two different notations that we learned for prime. Well, this one's prime notation, and this one is, I forget how to pronounce his name. I think it's Leibniz notation is what this one is called. Or they also call it differential notation sometimes. And likewise, v prime is dv over dx. Okay, so if we integrate both sides, here's what we get. So we're going to integrate this side, and what we end up with is something like, and I'm actually going to rearrange it first. We're going to end up with the integral of v times u prime with respect to x, because we derived with respect to x, plus the integral of u times v prime with respect to x. Okay, now remember, because we said u prime is du over dx and v prime is dv over dx, what happens is you have dv over dx times dx, and so the dx's cancel out and you're left with just dv. Likewise, your dx's would cancel out over here and leave you with du. And so you end up with something that looks like the integral of v du plus the integral of u dv. Okay, now if we do a bit of rearranging, what I'm going to do is I'm going to just flip these two. So such that we have uv is equal to the integral of u dv plus the integral of v du. And then we can rearrange it one step further and subtract v du from both sides, such that we can say the integral of u dv is equal to uv minus the integral of v du. Okay, so this is kind of what we established on Thursday, is our formula for integration by parts. So if we, when we worked this one out, we said we defined u as x, because that's our first part in the u dv, and therefore the dv part has to be the rest of it. Okay, so that means dv is equal to sine of x dx. Okay, and so we need to know what du is, because we're going to plug that in later. And we need to know what v is, because we're also going to plug that in later. So du is just the derivative of u. So if we take the derivative of x, that just gives us dx. If we integrate sine of x dx, we end up with negative cosine of x. Okay, and now we can plug it into our formula over here, and we can say u times v is x times negative cosine x. So I'm going to put the negative out here. So negative cosine x minus the integral of v du, where v is negative cosine x and du is just dx. Okay, and if we rewrite this a little bit, we get negative x cosine x plus the integral of cosine x dx. And now we can integrate this piece and say negative x cosine x. The integral of cosine is sine, so plus sine of x plus c. Don't forget to add your c. Okay, and this would be the integral of x sine of x with respect to x. Okay, so this is where we left off yesterday. So today we're going to pick up with this example. So it says sometimes you have to repeat the process. In other words, you're going to have to do your integration by parts more than once. Okay, so u in this case is equal to x squared. So that means that our du is equal to is equal to 2x dx. And so then our dv must therefore be e to the x dx. And the integral of e to the x is just e to the x. Okay, and now if we plug this in, what happens? Well, we have u times v, so x squared times e to the x minus the integral of v du. So that would be 2x e to the x dx. Okay. Now, we still don't know what this is. So we're going to have to do another integration by parts for this piece to find out the rest of our integral for the original one. So we're going to go over here and say u is equal to 2x. So du is equal to 2 dx. And then we're going to assign dv to e to the x dx, making v equal to e to the x. Okay, and so I'm going to go ahead and rewrite my integral down here. So we had x squared e to the x minus, okay, And now here we're going to fit in our formula again. So uv. So u times v is 2x e to the x minus the integral of v du. So 2 e to the x dx, close parentheses. Okay, and now we can do this one easy. So this becomes x squared e to the x minus 2x e to the x. Minus and a minus is a plus. The integral of 2e to the x is just 2e to the x. The dx goes away. And last but not least, our plus c. So our integral of x squared e to the x dx is equal to x squared e to the x minus 2x e to the x plus 2e to the x plus c. Okay. Give everyone a chance to catch up / write this down. So see, we had to do it once for this piece, but then because we still didn't know what that was, we had to do it one more time. And then it gave us a nice answer. Well, nice enough. If you wanted to, you could factor out the e to the x's. I think your calculator would do that if you plugged it into the calculator. It's not necessary though. Okay, so as it turns out, there is an easier way, well, there's a neater way to do this without having to do all of this work and make it look all, I guess it looks kind of messy because you have this u du dvv. There's a better way to organize it. So what the next question says is the following. It says a tabular approach is helpful with these repeated integration by parts problems. So it's the same problem again that we just had before, but we're going to attack it a little differently. So here's what your tabular approach looks like. So you're going to make a table, okay? And one side of the table will be labeled the other side of the table will be labeled dv. Okay, and so you'll have this table that looks like so. And on the u column, you're going to put what your u is to begin with. So x squared. And on the dv column, you'll put the other piece, e to the x, without the dx. And I'll explain why in a second. So the tabular approach is nice because it organizes everything, and you find the answer a lot faster by just organizing it this way. So down the u column, you're just going to take the derivative of your polynomial until you get to 0. So the derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 2 is 0. Down your dv column, you're going to integrate your function. So e to the x, the integral of e to the x is e to the x, the integral of e to the x is e to the x, the integral of e to the x is e to the x. Okay, so now that you've filled out your chart, you're going to start by placing signs on your u's. So you're going to change the sign, alternating each one, and you're going to start with a positive. So the first one will be a positive x squared. Your second will be a negative 2x. The third one will be a positive 2. And your last one will be negative. So you just alternate the signs. There's no such thing as a negative 0, really. But just out of habit. Positive, negative, positive, negative. Okay. So now what do you do? Well, now you're going to multiply your u diagonally across to your next dv. Okay, so you're going to multiply these that I'm drawing the arrows to. So in other words, the integral of x squared e to the x dx is simply x squared times e to the x minus 2x times e to the x plus 2 times e to the x plus c. And with that, you are done. Okay, and if we go back to what the answer was for the last problem, we see that our answer was, in fact, x squared times e to the x minus 2x e to the x plus 2 e to the x plus c. Okay, so you can do it this way, or you can do it this way. Now, what's the catch? Well, you can only do the tabular method whenever your u is a polynomial of some sort. And typically, you want to have a nice function on the right that you can integrate over and over and over again. You definitely can't use this method with something like the next problem, where you have a polynomial, but what's the integral of ln of x? Well, we don't really know what the integral of ln of x is. We know what the derivative of natural log of x is. We know that the derivative of natural log of x is 1 over x, but we don't know what its integral is. So in other words, your tabular approach only works whenever you have a polynomial to use for u, and you're going to derive it until you hit the 0. And then your second function usually needs to be a nice function. So a good place to use a tabular one like this is when you have a polynomial of a high order times, say like a trig function. That would be easy enough. Something like a cosine or a sine, that would just keep repeating itself, right? Cosine to sine, sine to cosine, and the signs would change every 2, so to speak. So you derive, you integrate, plus minus, always start out with positive, and then you multiply diagonally. Okay, and that gives you the same result as doing 2 integrations by part, or integration by parts. Okay, so like I said, if you were to try to use it in this case, you kind of run into a problem because this doesn't work out very nice. So how do we do this one? Well, this one we're just going to do the same exact way we did the last one. So we're going to say our u is, originally did the last one. Our u is x squared, so that means du is 2x. Our dv is, actually, I don't like this, because if we do dv, we would have to integrate natural log of x, and we don't know how to integrate that. So here's a good example of when sometimes you need to change which one is which, okay? And it doesn't matter how you change them. You should technically, well, you should and will get the same result. So in this case, we're actually going to name u natural log of x, because that way when we derive it, we get 1 over x dx. Easy enough. So dv is then x squared dx. So that means that v must be x cubed over 3. Okay. So now we plug everything into our formula. So our formula was u times v. So x cubed over 3 times natural log of x. U times v, v times u, doesn't matter. Minus integral of v du. So in this case, it would be x cubed over 3 times 1 over x dx. Okay, now we can rewrite this a little nicer. So x cubed over 3 natural log of x minus, I'm going to go ahead and pull out this 1/3. And then say integral of x cubed divided by x is just x squared dx. Okay, so x cubed over 3 natural log of x minus the integral of x squared is x cubed over 3. So this is x cubed over 9 because it's over 3 times 1/3. Plus c. Okay. So in some cases, as tempting as it may be to use the tabular approach, in some cases it's just easier to go back to your original integration by parts and solve it that way. Okay. If you have questions, I would suggest you write them down to ask me later, or ask a friend that does understand what's happening. Okay, and then we have 2 more to do. All right. So far we've been doing indefinite integrals, and those are pretty straightforward. But what happens when you get a definite integral and you have limits to worry about, right? Well, it says first integrate without them. So much like when you do a definite integral, you always integrate and then you evaluate, right? So don't worry about it. Let's just do our integration by parts, kind of like we did at the very beginning. So we've done this one already, but we'll do it again. U is equal to x, so that means that du is equal to dx. And then we can say that dv is equal to sine x dx, so that means that v must be negative cosine x. Okay, now here's where it changes just a little bit. The first part is u times v, so it was negative x cosine of x. And because this is done, we have to evaluate this from 0 to pi over 2. Now we subtract the integral from 0 to pi over 2 of v du. So negative cosine x dx. xd. Okay, so if we rewrite it, we have negative x cosine of x from 0 to pi over 2 plus the integral, I'm running out of space. the integral from 0 to pi over 2 of cosine of x dx. And so we'll rewrite it. Well, actually, let's go ahead and evaluate this one. F of b will be negative pi over 2 times 0. So, in other words, 0 minus f of a, which would be 0 times 1, so 0, plus the integral of cosine of x is sine of x from 0 to pi over 2. So, in other words, we're just dealing with sine of x now. So sine of x, sine of pi over 2 is 1, minus sine of 0, which is 0. So this should just be 1. Okay, so you follow all the steps that you do at first to get your du and your v. And then at that point, your uv is done, so you can evaluate uv from a to b. And then you have another integral where you want to keep your interval in as well. Okay, so not too hard. You just got to watch out for this one. Don't forget to plug it in here. Okay, and lastly, if we make it to this point in class, we'll do this one, this last one. It's a doozy. It's a lot of work, but it's really important. So I'm going to try to cover it. Well, I'm going to cover it regardless. And then if we need to go over it again on Monday, or if we need to finish it on Monday, we will. Okay. All right. So this one's a little interesting because you have to do your integration by parts at least 2 times, I think. And you can't use your tabular method because okay, got my mic back. We can't use the tabular method because you don't have a polynomial of any sort. So you just have to suck it up and use integration by parts as many times as you need to. So let's start with the first one. So I think because we use integration by parts, actually no, we have plenty of room over here to work with. Okay, so the first time, I'm going to say u is equal to cosine of 2x. And you might be asking, why not e to the x? Well, it goes back to which one is easier to derive. Now, if you integrate cosine of x, you have to get like 1/2 of sine of 2x, and you know, fractions aren't ever very nice to begin with. So let's just say we'll derive this one instead. So the derivative of that would be 2 negative 2. Oops. Negative 2 sine of 2x. All right, chain rule. Derivative of the outside times the inside of the inside times the derivative of the inside. Okay, so that's why we would get negative sine of 2x times 2. And then we have dv, which is, in this case, e to the x dx, xd. And then we have v, which is equal to e to the x. This is easy to integrate, so it's a lot easier to just use e to the x for our integration. Okay, so we plug it into our formula. So we're going to say u times v, so e to the x cosine of 2x minus the integral of v du, so e to the x minus 2 sine of 2x dx. Now, we run into the same problem again because we don't know what this is. So we're going to use integration by parts one more time. Okay, so I'm going to go down here and I'm going to say u is now equal to, we're going to use this one. So negative 2 sine of 2x. So that means that du is derivative of sine is cosine. Derivative of the inside is 2, so it'll be negative 4 cosine of 2x. dv, once again, is e to the x dx. And so therefore v must be just e to the x. Okay. Now here's where it gets a little messy. I'm going to go ahead and rewrite this integral down here. So the integral of e to the x cosine of 2x dx is equal to e to the x cosine of 2x minus uv, which is e to the x times negative 2 sine of 2x minus the integral of v du, which would be negative 4 e to the x cosine of 2x dx. Okay, so this is already starting to get messy. So integral of e to the x cosine of 2x dx is equal to e to the x cosine of 2x minus, actually plus 2e to the x sine of 2x, right? The negatives become positive. And here I'm going to say my plus, okay, this is plus 4, but then we have a negative out here. So negative, negative, negative gives us negative 4. I'm pulling out the 4. Integral of e to the x cosine of 2x dx. And at this point, if you haven't noticed it yet, wait a minute, we have the same integral we started out with. So, I mean, you could keep doing this over and over and over and over and over again. Or you can use some algebra. Now, we did some integration techniques like this maybe like 1 or 2 times a couple laps back. Now, we said we can treat this whole integral as just one variable. And so say this whole integral is just, I don't know, x. So this would be minus 4x, right? So algebra would tell us to add 4 to both sides. So we would get 5 integral of e to the x cosine of 2x dx, okay, is equal to e to the x cosine of 2x plus 2e to the x sine of 2x, and then we're left with, there should be technically a plus c at the end of all of these, so I'm just going to go ahead and add it now, plus c. Okay, so that's what we have now. However, we want to know what the integral of e to the x cosine of 2x is, not 5 times that. So now we're going to divide everything by 5. So that means the integral of e to the x cosine of 2x dx is equal to 1 over 5 e to the x cosine of 2x plus 2 over 5 e to the x sine of 2x. Technically this is c divided by 5, but remember, if you multiply, add, or subtract anything to a constant, it's still a constant. Okay, so your integral is 1/5 e to the x cosine of 2x plus 2/5 e to the x sine of 2x plus c. Okay, and that'll end our lesson on integration by parts.